On page 636, you have the sum and difference identity, which are complicated identities. First of all, you have two angles, so they go away from, if you have one angle, we like to use the Greek letter theta. But if you have two angles, then they introduce two new Greek letters for you. This is the Greek letter alpha, and this is the Greek letter beta. The beta is like a big B with a long part to it. So when I draw betas, I start at the bottom and make them that way to make them different than the letter B. So they're a little bit different than letter B. Alphas are pretty easy to do. You start at the top and swoop down. Oh. Reminds me of, they used to teach in elementary school. I don't think they do anymore, but they would teach, like, they would have a number 1 here with an arrow saying, this is where you have to start. And some kids who drew their alphas like this would get in trouble. Doesn't it look like the same letter? It is the same letter, but what happened the second time? I started at the bottom, and that was considered bad. They used to teach it in a certain order because it helped you when you got to handwriting. But they don't really teach handwriting anymore, so they were like, well, you can make things however you like now. They're not going to be super fussy. They used to be super fussy. Like, if you drew your alpha but started at the bottom, it would be wrong. You'd get in trouble. And if we go back in history of what kids used to get in trouble, who were left-handed kids? It used to be that you got in trouble if you wrote with your left hand, because that was wrong. Well, no, it's not wrong. Some people are left-handed. So, anyways, but I do like, I find, that's one of my favorite letters to make, is the beta. Okay, so these are some very big, scary-looking formulas that aren't bad, okay? The first thing, though, you have to realize is that you might be tempted to do something that is wrong. You might be tempted to do this. I'll do it in red. I'll put a big, it's not true, but you might be tempted to just do this. Wouldn't that be nice? Yes, it would be nice, but it's utterly wrong. It is not true. Okay? What are you allowed to distribute? Because this looks like something you do a lot in math. And you do a lot of distribution in math. Distribution works if the thing outside is a number, but sign is a function. You can't distribute functions. You can distribute numbers, but we can't distribute functions. Okay, this is going to cause some of you problems because you're going to want to distribute this function. Later on, we're going to do logarithms. It's another function. It also can't be distributed. You've seen this before, right? If I would square root, and it used to be on tests that they'd have to write it this way because they didn't have a computer that could write it correctly. Is this the same? No, you can't just square root 9 and you can't just square root 16. Right? This is saying the square root of the whole thing. It doesn't really come up as a problem with square roots because the square root function, you can just make the line longer if you need to, right? You're not able to, like, we don't write sine functions like this. Right? You can't group, I don't know. Yeah, I mean, we could invent something that makes it different than just brackets, but you're going to be tempted, just the way that it's written, to want to distribute it. However, this is not true. That sine of alpha plus beta is not sine of alpha plus sine of beta. We can test it by taking some that we know. I could do, I'm in radians. I'll just go into degrees, just so it makes it even easier to see, right? If I do sine of 30 degrees, plus sine of 45 degrees. Is that the same as sine of 30 plus 45, which of course I could just write 75, but I'm showing it just in the same form. Notice the numbers are different. It's not true. But according to this formula, sine of 30 plus 45 should be the same as sine of 30 cos of 45 plus cos of 30 sine of 45. Wow. But check it out, okay? So I just did sine of 30, and if I would do sine of 30 times cos of 45 plus cos of 30 times sine of 45, I get the exact same number. And your first idea is, okay, but why would you want to? That's a good question. Well, these formulas are going to allow us to do some more mental math, just what you wanted, with your unit circle. Some of you are perfectionists, and on your pie plate, did it bother you that there was a bigger gap here than there were gaps there? It's like, oh, wouldn't it be nice if there was another dot in between? Your pi over 12 family? Yes. We're going to be able to do our pi over 12 family without a calculator, but we need these formulas to do them, okay? You don't have to prove where these formulas come from. It's super fun and exciting, and I encourage you to look it up on Google. Why do the sum and difference identities work? We won't prove them in class, although here's a wonderful intuitive diagram that you would definitely think of drawing to figure it out, but no, we won't do that. Doesn't look. But one of the things we're going to do with our identities is get good at them first. So we're going to do this, normally we start with example 1. Today we are going to start with example 2 first. Obviously for AP Calculus you need to have all of your formulas memorized, this one included. For grade 12, I would say you just need to have it mostly memorized. By mostly memorized, what happens in a question is you get a question like 2a, which is sine 8x cos 3x minus cos 8x sine 3x, and you mostly memorize says, hey, I have a formula that has that, but I don't remember exactly which one. I should check my formula sheet. That's mostly memorized. At least being able to recognize the formula, and then when you look at your formula sheet, you can say, oh, on my formula sheet it says sine alpha minus beta is sine alpha cos beta minus cos alpha sine beta. So in this question, that matches up as the right-hand side. This would be the alpha, this is the beta, this is the alpha, this is the beta, with a minus sign in between. And if you have the right-hand side of any identity, you can substitute it into the left-hand side. That's the power of identities. You can switch things back and forth. So a quick and easy substitution would say, hey, I have the right-hand side of that formula. I can switch it to the left-hand side, which is sine of alpha, which happens to be the 8x, minus beta, which happens to be the 3x. And those are like terms. So I can get sine of 5x. Yes. They just explain it again. So I notice this part here is in this form of that formula on our formula sheet. So I put a little alpha and a little beta above. I can then rewrite it as the left-hand side of the formula, which is purple there. That's sine. Alpha was the 8x, beta was the 3x. And then those are just like terms, so I just simplified it to be 5x. Okay. So we have 4 big formulas for sine and for cosine. We also have 2 big formulas, and they're on page 638 for tangent. So if you look at your formulas for tangent on page 638, okay? The mostly memorized way of memorizing these is if you have a fraction with a whole bunch of tangents in it, check your formula sheet. That's the mostly memorized form. I'm like, ooh, there's fractions with a whole bunch of tangents. I should check my formula sheet. So when we go to the question we were working on, example 2, we'll do that tomorrow.